Hi everyone. Today we're going to talk about the section 14.4, which is how to find the center of mass and the moments of inertia. This section is another application of double integral. So first we look at how to find the mass. We already know that the general formula for mass is m equals to rho v, where rho is the density of the subject and v is the volume. In this case, rho is a function of xy, so we need to use the double integral under the area of our integration to find the value of mass. Let's take an example. In example 1, we have the question of getting the mass of the subject under the line y equals to 3 and above the line x equals to 2 over 3y. So we have the density function rho xy equals to 2x plus y. That means as long as the x and the y value changes, the density of this subject also change. That means we need to use the double integral to find the mass. So like here, we set up the double integral as 0 to 3 dy because we are doing the integration at the y-axis first, and then we do 0 to y over 3 dx. That means this distance is calculated by 2y over 3 minus 0. And we get the mass by solving this equation, and then the final answer is 10. And we can also use the polar coordinates to find some of the mass, like a circle or like a sphere. We can see that the problem here is to find the mass inside the area x squared plus y squared equals to 4. So this is clearly a polar coordinates problem. So we first need, and also the density function is given. So that means we need to use the polar coordinates plus the density function inside it to find the mass. So we convert the rectangular form into polar form as we already learned from 14.3. So on the graph, we can see that it goes from 0 to 2 pi over 2. So basically we wrote 0 pi over 2 first and d theta. And for r is from 0 to 2, which means 0 to dr. And inside it should be rho xy. To simplify this, we can get and don't forget to multiply the r after you put the density function, because that's how you convert a rectangular coordinate to polar coordinates, rectangular double integral to polar integrals. And if we solve this integral, we can get the mass of the object, and 4 pi k over 3 is the answer. And another question we're going to talk about is the moments and center of mass. So center of mass is where it is the point where we can just hold a subject when, like for example, like we use a pencil to hold the subject, and that's the point we want the pencil to be. So here's a figure like this one. So if you have a pencil and want to find a point where the subject can be balanced by a single point that the pencil will be held, this point is the center of mass. It's the balancing point of the subject. So let's first define how to find the moments and center of mass of variable density planar lambda. So the moment with respect to x is mx equals to the double integral under the area R, dA, and inside is y rho xy. And with respect to my is x rho xy. So notice that with respect to x, you have to multiply y, and with respect to y, you have to multiply x. So it's inversed. So that should be noticed. And if you want to find the center of mass, finally we divide the my by the mass and mx by the mass. And the mass can be calculated, as we already learned, by a double integral, rho and dA. And also notice that the x coordinates of the center of mass is equals to my divided by m. It's not mx, so this part is also reversed. So there's two reversal in this part, so it should be noticed when you have the problem like this. And here's an example of how to find the center of mass. So first we calculate the mass by using a double integral like we did just before. And the mass value equals to 256k over 15. And then we find the moment about the x-axis. Notice it's y multiplied ky, and ky is the rho function, which is the density function. So with respect to x, we multiply y with the density function. And then we get the y coordinates of the center of mass, because y coordinate is with respect to x divided by m. So this should be noticed. And the next part is the moments of inertia. The moment of inertia is the moment of inertia has two different versions. The first one is called the first moment, as we already learned, that with respect to x, we have to multiply y, and with respect to y, we have to multiply x. And the second moment is a little bit different. It's called the moment of inertia. So it's ix equals to y squared multiply the density function. So here it's y squared. So basically, if we use the first moment, it's just y or x. If we use the second moment, it's the y squared or x squared. And there's problems just directly ask us to find the moments of inertia. So we need to multiply y squared, not y. And there's another really important equation to remember in this section is r equals to square root I over m. And specifically, there is this, which is y equals to square root ix over m. And this r, or like the double bar y, double bar r, is the radius of gyration. So if the question is asking about find the radius of gyration to us, you have to use this equation. And notice that the double bar y equals to square root ix. So here is the with respect to x. So there's another reversal here. So you should notice this when you have the problems, like find the radius of gyration. And this is basically the section of 44.